In today's video, we're going to be looking at problem 912, sort an array, and we're going to be using heap sort. So as per usual, the 3 steps of solving a problem are 1, understand, 2, visualize, and 3, implement. So given an array of integers and nums, sort the array in ascending order and return it. You must solve the problem without using any built-in functions in O, n log n time complexity, and with the smallest space complexity possible. The constraints are that the number of the length of nums is between 1 and 5 times 104, and the value of each num can be between negative 5 times 104 and 5 times 104. And here we have an example, 5, 2, 3, 1. We want to make that 1, 2, 3, 5. Makes sense. So the key aspect of a heap sort algorithm is this process called heapifying. So there's 2 variants, min heap and max heap. And let me write this, min heap, max heap, and we call it heapify. Write that down. And the idea is that even though we're dealing with an array, we can actually visualize this more like a binary tree. So what would 5, 2, 3, 1 look like as a binary tree? Well, it would look something like this. So we have, this root node 5 has 2 children, 2 has a child 1. And so we're only talking about like max heap. Well, I guess I'll explain max heap and min heap. So max heap is where the root node is the largest number of the whole set or array, and then min heap is where the root node is the smallest number of the whole array or set. So if you look at this example that they gave us, 5, 2, 3, 1, this has already been max heapified. 5 is the root node and it's the largest. Like let's scramble these numbers a tiny bit so we get a sense of what the process is to actually like heapify an array. 1, 3, 2, 5. So what you want to do is you actually want to start from the right of the array and move your way down to index 0. So keep track of that here. And we have 1, 3, 2, 5. Okay, we want to create a sort of like heapifying algorithm that, and we're just going to run it on each node. So we're first going to run it on 5. Like there's no children. So the idea of like, well, I'll just show you an example with that running it like, so take like the root node 1. We want to compare it with its direct children. So 1, compare that with 3 and 2, and whoever's the largest node, like if it's not the root node, then we have to swap it. So in this case, we would have to swap 1 and 3. See, now 3 is the largest of this set here, of this group, and then now it's slightly more heapified. Obviously this 5 is not heapified, so just ignore for now. Now let's I'm going to show you why we want to start from the right. So let's do that process first with 5. It has no children, so we can move on. Next is 2. This 2 has no children, we can move on. So next up is 3. 3 actually does have a child, 5, and 5 is actually larger than 3. So what you want to do is swap those 2. And whenever you find that there's a discrepancy that you did have to swap, you then want to recursively iterate over the node that was changed to make sure that that is now properly heapified. As you can see, 5 has no oh sorry, did I 1, 3. I need to change it up here, sorry. Okay, so now you can see that 5 is larger than 3, so because we swapped it, and 3 has no children. And now we can iterate one more over. Compare 1 with 5 and 2. 5 is the largest number, so we can swap those 2. And we iterate over the next one. So 1 and 3. 3 is larger than 1, so we swap those 2. And now this array has been heapified, and you can see 5 is at the top, and that's all we want to do. And the general essence of what we want to do next is sort of like a 2-pointer problem. to do the final, final stretch of the implementation of actually sorting it. And I'm gonna now go back to 5231, which is our original example. So you want to have 2 points. So one is the like a J and an I, and J will. Well, so what we're gonna do is we're going to. You want to do like a swap with the leftmost node. So actually this will go here. We want to swap these two, and then because 5. So let's see what happens if I swap these two, 1 and 5. Now 5 is in its good final spot. It doesn't ever need to change again. So we can kind of lock it in place by moving this iterator down 1. So we will never heapify. We will never touch 5 again. It's good to go for our final answer. And then at this point, we want to run a heapification on these 3 numbers to get the largest number possible on the left side, so we can then flip it over to this spot right here. So let's see what that looks like. So we have 1, 2, 3. Let's heapify this. So we compare these 3 numbers. 3 is the largest one. So we swap those 2. And let's copy paste that over. So this is where we're at now. So we're actually at 3, 2, 1. Now we can swap the I iterator with the J iterator, and see 3 is now in its correct final position. We never need to touch it again. So let's move J down 1 again. So now we have very simple binary tree. So 1 and 2. 2 is larger, so we want to swap those 2. So we're looking like, and then we want to swap the I and J once more. And now we have our solution 1, 2, 3, 5. And this, we didn't use any extra memory. And this all happens in O(n) log n in terms of time complexity. So let's implement our max heapify algorithm. So max heapify, the inputs that it needs are, it needs an array, and it needs a parent node index. So let's call that index. And we need to figure out what its left node is and what its right node is. And obviously this sounds weird because we're dealing with an array, but the algorithm is actually pretty straightforward. Its left is actually I times 2 plus 1, and right is left plus 1. So if you look at 5, 2, 3, 1. So take the first number. Its index is 0. 0 times 2 is 0, plus 1 is 1. And then right is 2. So 1 plus 1 is 2. And then look at this guy, and I'll add one more number here. So this is 1. 1 times 2 plus 1 is 3. 0, 1, 2, 3. And then plus 1 is 4. So that's really all you need. And we need to keep track of, we're going to start off with a, best guess of what the largest number is between the 3. We're going to guess it's the, parent node. But now we have to prove it wrong. And I do have to mention that even though we have like these 3 main components that are max heapifying, and then we iterate from right to left to figure out the to get like a max heap going, and then finally we do another iteration from right to left where we lock in the largest numbers on the right side. We do have to, and remember how we have to do the lock-in process, we move J down by 1 gradually to make sure that we never touch it again. Well, the same process has to be added to the max heapification process. So imagine you have 1, 3, 2, 5. We've already locked in 5. Well, see, like in this case, like 1 and 3, these would swap. but now we would need, like if we don't like set up any kind of bounds, like 1 is less than 5, so 5 should be there, but 5 is already good to go. We need to like close it off, and so we actually have to start treating like have this idea of like bounds already in the max heapify algorithm. And the way do that is we just say, here are the bounds, nums on length, and if we're comparing child nodes with the parent node, we need to make sure that the left and right nodes are within bounds. Left is less than j, and so now we say, and our left is greater than our max. Well, then that means that max is now left. And exact same thing with the right node. And now we just see did max change. If max does not equal I, well, now we need to swap the two numbers. Left, right. That is just boilerplate stuff. And there you have it. We have a swap algorithm. And swap those two guys. And as you remember, we need to then heapify over the children of the node that got changed. And there, that should do the trick. So now we can move on to the first iteration from right to left to just get, the array in a max heapified format. So for let I equals j minus 1, I is greater than or equals to 0, I minus minus. Very simple. We just run our heapify. Oh, and we need to pass in our actual nums. And now we need to do the process where we take the left. If you remember what. So we had this example. Remember that this is already heapified. And the topmost node is 5, and in this case, we just need to swap this with the rightmost number. So 5, 2, 3, 1. So 5 swaps with 1, and now 5 is good to go. It never needs to change again. So we need to change the bounds of j so we just move it down by 1, and now 5 will never be touched again. It's locked in. It's good to go. And so with that in mind, let's just do exactly that. Oh, and by the way, you don't have to do it greater than or equals to. I'll just do like that. Slightly more efficient. And so we said we need to first swap. We just swap remember the leftmost number because it's already heapified with I. Now we need to lock it in. We never want to change again, so we move j down 1. And then finally we heapify. We need to heapify the leftmost number because take 5, 2, 3, 1. We have 5, 2, 3, 1. 5 swap with 1. And now we have 1, 2, 3, because remember 5 swap with 1, 1, 2, 3. See, this is obviously not heapified, so we need to run a heapify function so that we end up with this. See, 3 is at the top, and that'll be the leftmost node, so then we can swap that with the next rightmost number, and so forth. And with this in mind, everything should be sorted. So all that's left to do, let's get the right variable names and return nums. Let's see if we got this. So we got that one. Let's see if it passes. And there it passed. So there you have it. Catch you later.